Hello friends, welcome to my channel. Let's have a look at problem 958. Check completeness of a binary tree. In this video, we are going to share two classes of solution formats based on traversal algorithm. So in this video, I'm going to write the traversal algorithms in iterative format for details. So this problem asks us to determine if a given binary tree is a complete binary tree. So in CS or in a graph theory, a complete binary tree is a tree such that every level except possibly the last is completely filled, and all nodes in the last level are as far left as possible. So in other words, so if you have a right child in the last level but do not have a left child, it's not a complete binary tree. So here there are two examples given. So in the first example, so it is a complete tree. The reason is that there are three levels, and the first and second levels are in full state, and the last one is not. So if it were in full state, and the number of nodes should be 2 to the power 4, 2 to the power 2, that is 4. But for the subtree 3, so they have a left child, but they do not have a right child. So this is a legal complete tree. And in example 2, so similarly, but the third level is not full. So if in full state, it should have 4 nodes. But in this case, so the subtree 3 has a right subtree 7. Rather, it does not have a left subtree. Therefore, it's not a complete binary tree, because in the definition, as mentioned, in the last level, all the nodes should be as far left as possible, right? So the constraints for this problem are the following. First, it's on the number of nodes. In other words, the overall problem size. So the number of nodes is given by the closed interval 1 and 100. So 1 means that the overall tree is not null, and 100 tells us at most there are 100 nodes. In other words, the problem size is not that large. And secondly, the node values are in the range given by the closed interval 1 and 1000. So with that said, I guess we are ready to do the analysis. So in this video, we're going to share some solution based on binary tree traversal, or in general, a graph traversal. In order to do this problem, here are some points we need to notice. First, we need to notice or digest the definition of completeness in the binary tree, or in the complete binary tree. So this is the one thing. Another thing we want to notice is that the indexing or the counting. So here the conclusion is that if using one indexing, in other words, we start use the root as index 1, then if the parents have index p, then the left and the right children will have indices given by 2 times p and 2 times p plus 1. So for example, here this is 1, as the value also coincides with the index or indexing. Then the left child is 2, that is 1 times 2, and this one is 1 times 2 plus 1. So here's a comment, because sometimes some people prefer to use zero indexing. So if it were zero indexing, and then the parents has index p, then the two children will have index 2 times p plus 1 and 2 times p plus 2 respectively. So here let's use this one as example. So if the root 1 has index 0, so 2 will have index 1 and 3 will have index 2. So 0 is 2 times 0 plus 1 is 1. It's corresponding to the index for node 2. and 2 times 0 plus 2 will correspond to the indexing for node 3, right? So you can verify this. So here we're going to give two kinds of solutions. The first kind is going to use indexing to check, and the second one is going to use strictly the definition. So both are based on traversal. Therefore, if you are very familiar with tree traversal algorithms, so this problem should be rather routine or straightforward. So with that said, let's move forward. So here, first, I'm going to write one solution based on indexing. The reason is that if it's a full complete binary tree, so if I use all the indexing, then the length of the full tree, or in other words, the number of nodes, it should be equal to the indexing of the last node in the last level, right? So this is our overall thought. Then, in order to implement this, this is actually very routine. So here I'm going to use a queue. So let's first check a special case. Actually, it's not necessary. The reason is that here the number of nodes is at least 1. So, but let's make it. So if not root, so we're going to return true. We regard empty tree as a complete tree. So this is the one. And then we're going to initialize a collections deck. So I'm going to use this as a queue. So in other words, I'm going to do breadth first search, if you would like to say that. So here we can use this. So root. So here I'm using one indexing, right? So you can regard this one as indexing or coordinates. So here we are storing node and indexing, or index, if you like. So now the below will be standard traversal. So here first I'm going to write a one with larger space complexity. Then we just modify a little bit to save space. The result will store the node values, see, or coordinates, if we like. And then let's do the traversal. Well, Q. And then we're going to get the current node and the corresponding indexing. So the node and the coordinate, let's see, is Q pop left. So we are going to append at the end and pop at the very front. So this is this is using the queue behavior, right? So once we get this, what we're going to do is we are going to append this coordinate to the result list, and then what we are going to do is going to, if we check left first, if node left, let's see. If node left, what we are going to do is to append. So node left, and then the indexing will be 2 times the coordinate, right? So notice that here I'm using one indexing. If you put it here 0, you should write 2 times coordinate plus 1. That is corresponding to 0 indexing. So here the order is important in some sense. So node right. But for counting purpose, that makes no difference. So here I'm going to do node right, then 2 times coordinates and plus 1, right? So this way, actually, we can get all the node values, but the purpose is for counting. So what we are going to do is to return. So if the length of this result, this is the number of node, it should be equal to the coordinates in the last. So this should be in this one. This piece of code forms a solution format to this problem. Let's first do a check before moving forward. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the generic cases. So as we mentioned, due to the problem assumption, so we can comment out this. Let's do a check. Yeah, but it's actually good in general to keep this edge cases in mind. So this is one version. So here I'm going to copy this version and make some modifications to save some space. So here actually we use a lot of space in storing the node values. It's not necessary if we know the essence of the problem. So here, rather than store all the values, I just need to measure the length. So for this purpose, I'm going to initialize a list variable. It's called length, which is the number of nodes, and also I'm going to initialize a coordinate. So originally length is 0, and the coordinate let's use null. And then what we are going to do is, rather than do the append, what we are going to do is to each time corresponding to the append. So actually this length is incremented by 1. So I'm going to do this. And then I'm going to reset the coordinate. The coordinate is going to be the current coordinate. Then afterwards, so the last state of the coordinate should be equal to the length. So what we are going to do is to check if coordinate equals length. So this way, we just use constant space, and then in here, right, comparing with this line. And this forms another solution format. Let's do a check first. I'm going to change this one to be version v1. So let's check. Yeah, it passes all the cases. So this forms a class of solution to this problem. Next, I would like to present another kind of solution. Rather than considering the indexing, I'm going to use the definition in a more strict, more faithful way. So here, let me let's delete this part, and then I'm going to change this one as v1 1. Let's see, v2. So now let's use the definition. So when we use the definition again, so what we are going to do is to verify this one. So all nodes in the last level are as far left as possible. So here what we are going to do is, again, I'm going to use a deck. So it's collections deck. So here deck is corresponding to queue behavior. So we can do this directly. So but in general, we need to keep in mind. Sometimes we need to treat edge cases corresponding to null tree. And then in this case, what we are going to do, I'm going to introduce a flag variable called hasNull, initially false, and then we do the traversal. So here it's corresponding to sort of like a level order traversal. So here, let me first get the current length of this level, and then what we are going to do. So we are going to, for the current level, I'm going to use a dummy index for I in range m. So I'm going to get the current node as corresponding to pop left, and then we are going to check the state of the current to check if it's null or not. So if not current, in other words, it's null. So we're going to change this head null to be a true, right? We change the flag, then we continue. First time we meet this. And the next is the logic. What we're going to do, so if we have current right, so in other words, the right child is not null and not current left. So in this case, no matter we occur this situation, we meet this situation in any level, so we should return false because it's actually already not a complete tree. And another case is if head null, right, and current. So we also need to return false. So after we do this check, so this corresponding to the core logic or core definition of the completeness in a complete binary tree. So next we are going to add the left child or right child depending on, but in this situation, here in the solution above, so if the node is not null, then we are going to enqueue. So here, no matter it's null or not, due to the logic here, we need to enqueue. So here we are going to append current left, queue append current right. Yeah. So this way, if after we finish this while loop, nothing has returned, so we're going to return true. In other words, the tree is indeed a complete binary tree. This is the second kind of solution format. So in this way, so we're still using traversal. So more precisely here is a level order traversal. It's still breadth first search and breadth first traversal, I would say. And here the difference is that when we do the enqueue operations, so we are not we do not care if it's null or not. We need to enqueue the corresponding subtrees. So yeah, I guess before we move forward, let me check this solution. Yeah, it passes all the cases. Now let's look at the generic case. Yeah, it passes all the cases. So with that said, I guess that's about it for this specific problem. So actually, as an extension, you can think of recursive solutions to this problem, because tree or binary tree is a recursive data structure or data type. So in this video, we presented two kinds of solutions based on traversal in iterative format. So yeah, if you find this video useful or informative, you're welcome to follow up our channel or share this channel with your friends. With that said, thank you.